We're practicing our properties of integrals here. Hopefully much of this will be very visual for you. Here we're adding the integral from 3 to 11 and then picking up with 11 to 13. So we may as well do this as one interval from 3 all the way to 13. And in the next problem we have the same situation where we go from 3 to 11 and then 11 to 8. So here this interval is actually going from right to left, so it is actually going to take away some of the area. So 3 to 11 and then backwards from 11 to 8, but it works out nicely that we just use the limit that we start with and the limit that we end with. Regardless of the order, it always works. Okay, if we know that the integral from 3 to 11 is w, then what is the value from 11 to 3? That would be the opposite of w. The area from 8 to 8 would always be nothing, 0. In question 5, we have a horizontal constant function from 3 to 11. So we've talked about use your geometry when we have a constant horizontal line here. So our b minus a tells us this rectangle has a base of 8, and of course it has a height of 5. So use geometry whenever it turns out to be faster than doing the antiderivative. The fundamental theorem would work as well. If we did the fundamental theorem, the antiderivative of 5 would be 5x. Evaluate from 3 to 11, and we would simply have 55 minus 15. So of course the fundamental theorem would also work. Okay, so in 6 we're simply going right to left from 11 to 3. So instead of positive 40, we'll have negative 40. In question 7, we're back to going from 3 to 11 as expected, but this time our function is at y equals negative 5. So from 3 to 11, our base is still positive 8, but our height is now negative 5. So this area would be negative 40. And then in number 8, what are we really thinking of here? We're reversing the limits. So this time we're measuring right to left, so our base would be negative 8 and our height would be negative 5. So there's a good visual explanation. So we really have a double negative situation to give us an integral equal to 40. In number 9, we know the integral from p to q is given to be n. So look at a. We go from p to r plus the integral from r to q. So since we pick up where we left off, this is going to give us the integral from p to q. And that's our given value. So our answer would be n. In the next one, we reverse a little bit, but notice that we pick up from q to q. So we will end up with the integral from p to r. And that's the best we can do, I guess. We don't know a value for that. In C, the difference here is that we've got a multiplier of 7. So just like we could do the multiple after we did the derivative, the same property is true for integrals. So we could do the integral first and then multiply by 7. So we can see that this would give us a 7n. And here again an integral from p to p, another no area. Here we have an even function, symmetry to the y-axis. So if we are told that the shaded area is m square units, then this other side would also be m square units. So we can double the area to get 2m if we're going from negative a to positive a. 11 is an odd function, symmetry to the origin. So we're going from negative a to positive a. Well, this area, whatever it is, we'll call it n. And this area would be negative n. So we would cancel out those areas to get 0. All right, instead of doing the fundamental theorem here, we're asked to think about these visually. and it will save you some serious time. You don't have to, hopefully you're just going to be visualizing these. You don't actually have to draw them on your paper, at least not the next time you see them. So remember that sine is an odd function. In fact, we actually know that this area is 1 and we know this area is -1. But all we have to know is that it's an odd function, so we're going to come up with an answer of 0. The absolute value function use triangles. So if we go over to 2, we know that this value is at 2, 2, and this value is at -2, or this point is at -2, 2. So you could find one of the triangles and double it, or of course you could say those two triangles together make a 2 by 2 square. So if you did 1/2 base times height, of course, for each of these, each of the triangles is going to have an area of 2. So the entire integral would have an area of 4. A couple of different ideas here for c. You could either leave 3x, or you could bring the 3 to the outside and make it even simpler. So the integral of x, think of the line y equals x. You know graphically what that looks like. It's the 45-degree line, and it is an odd function. We don't really need that for 0 to 5. So our line y equals x. So if we go from 0 to 5, this point is 5, 5. So our base is 5 and our height is 5. So the area of this triangle would be 25 halves. And then don't forget that we've got to do this 3 times the integral. So there's one method of getting 75 halves. Could you do the fundamental theorem? Of course you could. You could raise the exponent to 2 and divide by it, and then you could evaluate from 0 to 5. So putting 5 in there, there's your 75 halves minus 0. So of course fundamental theorem also works. Letter D, if it goes from -5 to 5 and it's an odd function, don't stop to think about it. If you know it's an odd function, make sure you use that property. This is our symbol for greatest integer function. So we're going from 0 over to 3. So then we jump up here to 1. So this is the point 1, 1. And then we jump up here to 2. And we would stop here at 3, 2. So the integral is pretty clearly just these rectangles. The first rectangle is actually just a segment, so it has an area of 0. This is a 1 by 1, so it has an area of 1. And the next one is a 1 by 2. So altogether here we have an area equal to 3 units. All right. Again, your common functions, remember that if you pick a number bigger than or equal to 2, you're going to get a value of 1. And if you pick a number smaller than 2, you're going to get a value of -1. So now we want to do the area from 0 to 6. So from 0 over to -2, and then we would jump up here to go from 2 to 6. So let's think of these two rectangles. Here, below the axis, we have a 2 by 1. So that, and I want to make sure I can see that that's a -2. And here we have a width of 4 and a height of 1. So we've got a -2 area and a positive 4 area. All right, letter G, if you're asked to use geometry, you know that this line, y equals 3x minus 6, and I better give myself some more room there, has a y-intercept at -6 and a slope of 3, so rise 3, run 1. So it has an x-intercept at 2, and we want to go from -2. So think what happens if you put -2 into this function. You'll have -12. And we want to stop at 5. So if we put 5 into that function, 15 minus 6 would be 9. So could we simply add two triangles, which mine look congruent, but they might not be. Let's double check. This triangle has a base of 4 and a height of negative 12. So its area would be negative 24. And this triangle has a base of 3 and a height of positive 9. So it has an area of 27 halves. So negative 48 halves and positive 27 halves should give us what? More negative 21 halves if we add those two values together. Okay, don't spend any time on H, look carefully. Same problem as G, but we've reversed the limits. So we had a negative area, so now we have a positive area. And in I, we have negative 19 to positive 19 of x cubed. So again, there's the visual picture, but we can see it's an odd function. So area of 0 because of the symmetry to the origin. Our cosine wave from negative pi over 2 to 3 halves pi. We've already done this. We know that each of these areas would be 1 and each of these areas would be negative 1. So use what you've done before to save time. Could you, if you forgot that, could you do the fundamental theorem? Of course, that would be fine. All right, another absolute value, but this time it's shifted 2 units to the right. So there's our corner, and we're going to negative 1. So this point is at negative 1, positive 1. And over to 8, put 8 into that function, and we'll have 8 comma 6. So two different triangles to add up. So this triangle, this point is at 2, 0. This point is at 8, 0. So this triangle has a base of 3 and a height of, let me try that again. I think I wrote this wrong here. Let's put negative 1 in here. Shouldn't we have a height of 3? These have to be 45. 45 triangles is how I caught that mistake. If the slope is 1, don't these have to be isosceles? So the base and the height of this side are both 3's. And here we go from 2 to 8, so the base and the height of this side are both 6's. So we have 9 halves and 36 halves, which of course is 18, but I might as well leave the common denominator. We can write this as 45 halves or 22.5, your choice. We're thinking geometry here, so think about this square root. If we square both sides, remember that this was half of a circle. So you have to remember your common functions. So this is a circle with a radius of 3 and a center at the origin. And we're only doing the positive root or the principal root. So remember what this is. This is the top semicircle of a circle with radius of 3. And we're interested in the integral simply from 0 to 3. So geometrically, we are doing 1/4 of a circle. So use 1/4 of pi r squared. So 1/4 of pi times 3 squared, and we'll get 9/4 pi for our answer. Don't forget the pi symbol. Question 13. We're adding up rectangles. F of x is the height of each rectangle. Delta x is the base of each rectangle. So this is a Riemann sum, and we're letting the number of rectangles go to infinity. An infinite Riemann sum is the very definition of integral. So if we're going from A to B, this question is not asking you to do any work. Just do you know that this is the definition of an integral. So as soon as we do an infinite number of rectangles, we get the exact area. All right. So some practice here with average height. Don't make this more complicated than it is. If we know that the region is 24, we don't even know what the function is. So hypothetically speaking, I could just draw something like this, but it could be any kind of function. So this is really what's given for us. So the average height is, could you shave some of this off? Could you find a place where you could shave this into a rectangle that has the same area? So can you see that b minus a here is the width of our interval 8, and if the integral gave an area of 24, then we would want this red rectangle to have an area of 24. So if the base is 8, then our average height would have to be 3. So height average would have to be 3. And that's what the MVT for integrals is all about. MVT for definite integrals. So here we have to do one algebraically. So let's do our fundamental theorem. We know the antiderivative of 3x squared is x cubed. Evaluate from negative 1 to 3, and we'll have 3 cubed minus negative 1 cubed. 27 minus 1. Let's try that again. 27 minus a negative 1. So we'll come up with 28. Now, what we're interested in here is, and you know what this is, you know this is a parabola that we're going from negative 1 over to 3. You don't have to graph this, but now what you know, we just did the integral, so you just found this red shaded area to be 28. So MVT is saying, well, what could you do here? You could find some place where you could shave off some of that upper value and fill in to get a rectangle that has the same area. And I think that's a little high where I picked that point, but you've got the idea that our average height, our h sub av, is simply going to take the width of the interval here. That's silly. Negative 1 to 3 is 4. So we want this blue rectangle to have the same area. So if we want 4 times the average height to give us the same area of 28, do you see that the average height would have to be 7? So now we're looking for the c value. So we're saying for MVT, for integrals, where is f of c equal to the average height? So our function is 3x squared, so we want to substitute c into it. And where is the average height equal to 7? So we would get the plus or minus the square root of 7/3. Don't forget that there would be 2 of them, but negative square root of 7/3 is over here. It's outside of our interval. So we're only going to keep the positive because we're interested in the interval from negative 1 to 3. So we would only have one value of c that fits in that interval. All right, so question 16. Same function, and it says on negative 1 to 3. Well, that's the same interval. Where does, or at what value of x does this function achieve its average height? Trick question. This is the same question as number 15. So it's just worded in another way. All right, a little practice with your calculator. We are going to do a midpoint Riemann sum using 4 equal partitions. So we're going from 1 to 9. Think what this square root graph looks like. What would you put for x if you wanted that to equal 0? You'd have to pick negative 1.5, right? And that's a 1.5. If we put 0 in for x, we'd be at the square root of 3. So we kind of know the shape of this graph. Square root graphs are slow risers. So you don't have to be this precise. You guys could do this probably without a diagram at all, but now we want to do the interval from 1 to 9, and we would like to divide it into 3 rectangles. And we're measuring the height of these rectangles at the midpoints. So you've seen this before. We're going to measure the heights of the rectangles at the midpoints. And of course, you know that our delta x, I hope you know that our delta x is always b minus a over n. The width of our interval is 8. And we're chopping it up into 4 rectangles. Oops, I only chopped it into 3 rectangles. Darn. We're supposed to be doing 4. That's even easier, however. Let me go back to scratch. 1 to 9. I like that even better because then our delta x will be 2. So we want to start at 1 and jump by 2's. So 1, 3, 5, 7, 9. But we're actually measuring the height in the middle. So we're actually measuring the height at 2, f of 2. And then the next rectangle, the midpoint would be at 4. So you've got the idea here. So our M4 value would be our delta x of 2 times the height of each rectangle. So f of 2, f of 4, f of 5, nope, so f of 6, and f of 8. Okay, and then you can do some of that arithmetic by hand, or you could go right to your calculator, put the function into your calculator, and I have approximately 28.389. All right, and now we're to change our calculation, so we're doing the same partition, but we're measuring at the left-hand side. So now we want to do L4. So our delta x is still 2, but we're measuring the heights at the left-hand side of each partition. So f of 1, f of 3, f of 5, and f of 7. And again, on your calculator, this would be a y1 of 1, a y1 of 3, and so on. And I have approximately 25.929. All right, so for an increasing function, like the one we just did, what do we know about right-hand rectangles? Well, right-hand rectangles would be above the graph. So right-hand rectangles would give us an overestimate. And what about left-hand rectangles? Left-hand rectangles would be below. So left-hand rectangles would be too small, so they would give us an underestimate. And, oops, I presumed what that question would be. Let's read it again, sorry. Decreasing function. Let's draw a decreasing function. And now let's do left hand. I tricked myself the way I typed that question. So now when the graph is decreasing, then the rectangles from the left edge will also be overestimate. So read the question carefully to draw your picture. And I guess that should do it.